Greetings there, peeps. What we're looking at today are a couple of concepts that are related to hydrostatics. One of them is gauge pressure. So what does it mean when we connect a gauge up to a pump? What is it actually reading for us? And how does that relate to hydrostatics? We're also going to look at something called Pascal's principle. So hopefully another short video here with just a couple of key concepts. First one is gauge pressure. So we saw this last time, this relationship here between pressure 2 is equal to some initial pressure, P1, plus rho GH. So it's related to the height of the fluid, the density of that fluid, and of course the acceleration due to gravity. So this is the generic way to write what we were looking at before. Now, P1 though is often atmospheric pressure. So we saw that modeled actually in the last video as well with the floating box in atmospheric pressure on top of it. P2 is considered to be absolute pressure, okay? So absolute pressure over here is, well, the addition of atmospheric pressure in most cases, plus something called gauge pressure. So the difference between the two, we saw this for this quantity over here, we have P2 minus P1. That's called gauge pressure. So that would be what the tire gauge on, let's say, an air pump would read, and usually that's in PSI, that's the, which is pounds per square inch. In our everyday lives in America, at least, it would read pounds per square inch. So if you ever used a pump like this one, this is just a little bike pump, an emergency pump. But if you ever use an actual pump, you'll notice that a lot of them have gauges on it, and they tell you something. They don't tell you the absolute pressure, that it really is a subtraction from atmospheric pressure. Here's why. Well, inside here, we have an enclosed box, and in that box is some gas that's producing some kind of pressure. Now, gas can produce pressure as well. The difference between gas and a fluid, though, is that the gas can be compressed using relationships like Pervnert, right? Fluids we'll consider to be incompressible, and that's going to be really key when we discuss the next concept of Pascal's principle. But here we go. Here's a gas, and it's got some pressure, and it's pushing out this fluid that's going to raise in this tube over here as much as it can based on the pressure inside. If the pressure increases, like you heat this up, this meter goes up. This is a gauge. And with the height going up, the pressure must be up. All right? So really, what we're seeing here is that this change in height would tell us something about the change in pressure, and that's what the gauge would read. But the gauge, is just this height difference over here, just the rho GH for this enclosed system. But oftentimes we've got to consider that, hey, we're on Earth and we need to consider this atmospheric pressure. So the gauge connected to this box over here is based on the height of the fluid that's pushed upwards. Fantastic. Hey, greetings peeps. Pascal's principle. All right. One of the conditions of Pascal's principle is that fluids, such as water, are considered to be incompressible. Basically, you try to squeeze them as much as possible, they will not change their volume, their density will not change. Their density remains constant as the pressure increases. That's really key. That's much different than a gas. So it's going to allow us to do some interesting things. Also, pressure changes in an enclosed fluid is fully transmitted through that fluid. So if the pressure changes in the fluid, you're going to feel that everywhere. So suddenly, for example, if you were to be swimming in a pool underwater and suddenly something like some big metal plate the size of the pool were pushing down, you would totally feel that because that pressure is transmitted everywhere. So what we have here is a hydraulic piston and lift. And Pascal's principle is this interesting relationship between what happens when you have this like thin tube over here with area 1 and a large tube with area 2. What we have here are movable pistons. So if we apply a force down here, it's going to press this fluid down and push it. And up here, we've got just kind of like a solid piston that is allowed to move upward. Okay, so these are both movable pistons. Now, over here, where I've got this dotted line, there's equal pressure at the same height, because the same height, of course, rho GH, if the height is the same, you've got the same pressure in the fluid because the fluid is here and the fluid is here. Okay, so this we'll call P1 and this is called P2. All right, so now what happens is that F1 presses downwards. And F1 will therefore increase the pressure in the fluid, which is transmitted throughout. So if I press down over here, if we remember before, that P1, that initial factor P1, if that increases, then this pressure here increases. And if pressure is transmitted throughout the fluid, P2 increases as well by the same amount. Okay, that's really what it means, that pressure in the fluid is going to be transmitted throughout. So P1 at this height, same height, equals P2. Now we can consider this in terms of forces and areas, because pressure is force over area. This is Pascal's law, really. F1 over A1, so that's pressure 1, equals F2 over A2, pressure 2. Now, A2 is way bigger than A1, and that's really significant over here, because what we get is this. If we solve this for F2, F2 is just going to be A2 divided by A1 times F1. See, over here we got A2 in the denominator, multiply both sides by A2, and you get this. So there's this ratio here of A2 and A1, and that leads to the amplification of force F1 based on this ratio. So in other words, if A2 is way larger than A1, you're going to get, let's say it's 100 to 1, your diameter or your area is 100 times larger, you're going to have a force that's 100 times greater over here at F2. That's really cool, and that's really amazing. Here's why. It enables us to create things like hydraulic lifts for repairing cars. If you want a car to be lifted, or just your jack to repair a tire, you want to be able to amplify the force somehow that you put in order to get a big force out. Now, that's not something for nothing, okay? Because in this little tube, you're going to press this a large distance over here, and the water is barely going to lift this big area up. Very little, because it has more capacity, a larger volume to fill. So you have to do this multiple times. Either you have one wicked tall tube over here that you thrust downwards, or you do this in short increments. And that's what a pump is. That's what your jack is, essentially. It's just pushing the fluid many, many times so that you get the fluid to push this guy up, 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 up. But the idea is that you're creating an incredible amount of force by putting very little in. So again, not something for nothing, but it's kind of like in torque, where you have a longer lever arm, so it's easier to rotate something. However, you're rotating it a much larger rotation. The distance that the lever arm moves is much greater. So it's kind of the same concept there, where force is amplified, but you've got to, the sacrifice is to push it down much, much more in terms of its length. All right, and that's Pascal's principle. So hydraulic lifts are a part of that. We'll see some demonstrations in class. All right, that's all I got this time. Next time it's Archimedes' principle. So here we go. More right out. Out.